Welcome to Fly Industries and an overview of our development process of our drone Onyx and our use of it as a test platform for 3D printed custom toroidal propellers. So we're going to start with the first prototype that we made back in July. This is of course the current prototype, and we've already have a video going over this, our launch video. And it talks about all the technical specs and the build as it is now. And this is our final iteration of our toroidal props. But it didn't always look like that. This was the first prototype ever of Onyx. This was made back in July of 2024. Started working on this when this project was first an idea. And this had a lot of different ideas than the current version. We wanted to use a Raspberry Pi as a flight computer. And we were originally going to have a Pixhawk and a Spectrum flight controller just to prevent any radio fail-safes. And the whole thing was just going to be a lot bigger and bulkier than the current version is today. So that wasn't always the case. Eventually, when we got a little smarter and a little more knowledgeable about drones, we realized, wow, a flight controller and another flight controller to act as a receiver actually wasn't a great idea. So we switched to this prototype here, which is originally going to be cut out of carbon fiber, but due to budget issues, we did not, and the arms are always going to be 3D printed. This is our first prototype, and there's a little GPS mount that was much too small because we didn't realize how big our GPS was. We were originally going to have this cut out with another layer double stacked of carbon fiber, and that's where we would mount our flight controller and our camera. But we moved on from that design very quickly. It didn't last very long, and we soon moved on to this prototype right here. This prototype is down a bunch of pieces. The arms are all relatively the same, but the big change is the chassis. We realized that we were going to have a 3D printed chassis through and through, and we wanted a lot of features on it. So this chassis is actually split into two parts for ease of 3D printing. We have the main body here and the battery tray here, and those go together right like that. It fits in with the reinforcement ridges, and it fits in with 6 M2 by 12 millimeter screws. And on the top here is where the most interesting happens. First of all, there's a GoPro mount that we could mount this GoPro Hero 11 to and fly with it and use it as a camera. And we had a cover for the flight controller and a mount for our GPS. The GPS would go here, and this hole was originally for our receiver. Our receiver was going to be mounted here with wires running out the back like that. And the arms were the same as for the first prototype. Now, the next prototype was also very similar, but there were some changes in the arms and in the cover for the flight controller. This is the old cover, this was the new cover. This cover actually had a hole in it for an LED to run out up to the top so we could figure out which way the drone was facing front, and was also much longer to accommodate the second flight controller because we went back to that idea for this prototype just to see if it would work. The rest of it was relatively the same with the same chassis design. These channels, by the way, are for wires from the ESCs at the front. They would run back to the PDB that was going to be mounted back here, and this is where our battery plug would come out of. The arms were relatively the same, except they were made a little bit shorter and had a little bit deeper of a motor mount. The next version of our prototype was actually the biggest change in the arms. This is the only arm we printed out because we realized how much better this design was and just jumped right to it. This arm is about an inch shorter in length and features this piece right here. This is for strength because during testing, we realized that our frame was bending a lot at the arms, and so we added this to accommodate a 14 millimeter bolt that went all the way through, and this really stiffened up our arm and our frames and reduced a lot of vibrations that we were having. Now that leads us to our next full prototype, which is this right here. It has a lot of changes in it. First of all, the battery mount is the same, but it's completely enclosed now. There is different ridge lines on the front of the chassis to make it stronger. There is no tab above here anymore. All the arms have a strengthening point, but the biggest change is actually the camera mount. We were going to have a versatile GoPro mount here that had different angled wedges, so our GoPro could be mounted at different angles that stayed consistent when we took it on and off. Now, our last prototype and our final bit of changes is actually this failed chassis right here. You can see it peeled off the print bed, but this is our biggest change to the chassis by far because we actually extended the front by 20 millimeters and added this part right here. And this is a 20 by 20 grid pattern to take our Walksnail VTX, so we could mount it directly to the front of the frame. And this chassis has those holes in it, but the print just failed. But after that, we moved on to our SLS printer prototype. And the biggest problem we had with our SLS printer prototype was landing gear. So we actually went through 2 iterations of that. We have this first iteration here and these 2 here. These are what we currently have on the drone, except the plate is just a bit thicker. But this one is actually the most interesting one. It mounts where our arms mount. It was inspired by the lunar rover and uses progressive geometry to be really soft here and much more difficult to press here, giving us a soft landing off the top, but still good enough squish for hard landings. But we ended up not using this because of how complicated it was, how much simpler and easier these were, and how replaceable these were if something broke. Now, the next thing that we moved on to after landing gear was actually covers. Now, this is the first prototype of our cover. It was printed like this to save on filament. And this is the second prototype, which has a couple small changes, like the holes up here, and was printed more upright to be a better version, lighter version with more airflow. Now, these prototypes both fit on the full-size Onyx drone, but they were not the only changes we had to make to accommodate the cover. This is our new GPS mount. As you can see, there used to be a 25mm extruded circle there to mount our GPS, but we no longer have that due to wanting to maintain a sleeker profile. And you may be asking why the GoPro is still here. And that is because we still wanted to mount a GoPro, even though we had our camera now where it used to be. So now what we do is we have a 3D printed part that actually mounts onto these 4 screws here and carries our GoPro underneath just like this, right in front of the battery. So, but what did we, no wait. And that was all of our Onyx prototypes. Yeah. Onyx was actually used as a test platform to develop these. These are our 3D printed toroidal propellers, but these did not always look like this. This is our final version as of today, and this is what we actually fly on the drone. But we started all the way back when Onyx started in development with these. These are 4-inch toroidal props, just like the MIT design, that are very low pitch. They were super heavy, super inefficient, and produced almost no thrust. But as we've gotten better, we started to learn a little bit, so we made the propeller much bigger. This is actually a 5-inch version of the same prop. The pitch is a little more aggressive to produce a little more thrust, but it still sucked overall. So we got a little smarter and decided to try a bi-blade version because we knew that bi-blade propellers were much more efficient and wanted to try our hand at it. We couldn't quite get the CAD to work, so it's kind of got this goofy section here where it kind of overextends past the center, but it's all right because they didn't end up working very well anyway. But then we moved to a more custom design of our toroidal prop. This is actually our first ever prototype of it, and we made the blades way too thin and flexible. And this is super flexible, super light, produced literally no thrust. But we improved upon our design with this next iteration right here. Much thicker, much more rigid, produced more thrust, but it didn't produce it in a centralized location. It was often pushing just air everywhere, acting more like an impeller than a propeller. So we moved on to a much bigger design, a 7-inch platform, and these were much better. They produced much more thrust, but our pitch angle was still very low and we weren't getting much thrust, although we were getting good efficiency. We were also still throwing a lot of air everywhere, working the propeller like an impeller. So we moved to a 3-bladed version, hoping to centralize our thrust a little more and produce a little more to lift our quad off the ground, but these ended up not working as well as we wanted them to due to the same problem of just throwing air everywhere. So we developed this version. This is the 3-bladed version of our final prototype here. And what's really unique about these propellers is that they actually bow down slightly. So on a completely flat surface, the center of the propeller doesn't actually touch the ground and instead can flex down just a little bit. And what this does is that actually vectors our thrust from the propeller. Instead of throwing air out like this, it throws it in a more cylindrical shape. And the more cylindrical that shape is, the more efficient our propeller can be at producing thrust for our drone. And we made this 3-bladed version, we tested them, and then we made a 2-bladed version to improve our efficiency. Now I'm going to hand things over to my partner to explain the math and physics behind these propellers and why they work so much better than these propellers.
So to elaborate on that a little bit more, what we have with our custom designed toroidal bi-blade propellers is that the pitch on these is actually shallower than these HQ propellers. And what that does is it means they don't produce as much thrust as the HQ ones, but they are more efficient, and which means they're quieter. So we like that a lot more. And another thing about these is that we couldn't replicate the twist along the cord here in our CAD software. So to compensate for this, we added a bow. And what that does is it throws the air in a cylindrical cone underneath it instead of outward, which we liked. So to get into the math behind this, during testing, we found that these 7040 HQ props produced an average decibel rating of about 79 decibels, while our custom designed bi-blade toroidal props averaged about 74. So we can do some math to find the percentage increase between these two. And this math actually works because the decibel scale is logarithmic, which means we can use the inverse log to find our percentage increase. So the formula we're going to use here is 10 to the power of b minus a over 10. And b has to be greater than a for this to work. So in this case, b is 79, which is our HQ propellers, while a is 74, which is our custom bly blades. So we do 10 to the power of 79 minus 74 over 10, which comes out to 10 to the power of 5 over 10, or 10 to the power of a half, which is just square root 10, and we get, plugging this into a calculator, we get the number 3.16. So to turn this from a decimal to percentage, we just do times 100 to get 316%. So in the end, we found that our custom bly blades are 316% quieter than the standard HQ propellers.
Thank you for watching our video about Onyx. We're going to leave you with a little clip of us spinning the props so you guys can actually hear them in action, and come back next time for more.